Alpha decay, instead of being a ray, is actually a stream of particles. More specifically, the particles are a helium-4 nucleus. Helium has an atomic number of 2, so it has 2 protons, which gives the nucleus 2 positive charges. It also has 2 neutrons, which do not have a charge. Since it is just a helium-4 nucleus, there are no electrons. In order to give off an alpha particle, it typically must be a pretty large atom to begin with. We refer to the original unstable atom as the parent atom. This parent atom decays into what is known as the daughter atom. In the case of alpha decay, the parent atom is losing a helium nucleus that includes 2 protons. Remember that protons are what actually defines the element. So if the parent atom loses 2 protons, it changes into a completely different element. Say we have plutonium-239 undergoing alpha decay. Plutonium has an atomic number of 94, so losing 2 protons would result in a new atomic number of 92, which is the element uranium. Now, a helium-4 nucleus also has 2 neutrons. This gives it a total of 4 nucleons that would be lost from the parent atom. In our plutonium example, then, instead of 239, the new atom would have 235 as its mass number. So our parent atom of plutonium-239 undergoes alpha decay and becomes uranium-235 and a helium nucleus. Now, at first glance, you might look at that and confidently say that mass is conserved. In reality, this is kind of what happens, but not really. The release of an alpha particle also releases energy, so actually the sum of the masses of the alpha particle and the daughter atom will be just a little bit less than the mass of the original parent atom. This is actually why the decay occurs, because nature likes lower energy. So the unstable nuclei lose mass in order to lower the energy of its nucleus. We can actually determine the amount of energy released from the decay of an alpha particle by looking at the relationship between mass and energy. In this case, E would represent the change in energy in the nuclear reaction, and delta M would be the change in mass between the parent atom and the final products. Take our example decay equation. Plutonium-239 decays into a uranium-235 and an alpha particle. We can start with a change in mass, which remember is final minus initial. The mass of the atom is just that, the unified atomic mass, so we would have to look up those values on a periodic table. Our final mass is the mass of the uranium added to the mass of the alpha particle. Our initial mass is the mass of the plutonium atom. Subtract those and you get a very small change in mass of 0.0005631 unified mass units. Plug in that change in mass and convert it into mega electron volts, and we get 5.25 mega electron volts of energy given off by the decay of plutonium-239. This amount of energy is about 1,000,000 times more than the energy of a typical chemical reaction, and most of it becomes the kinetic energy of the alpha particle as it moves away from the parent atom.